Hello everyone. I wanted to go over Taylor series in further detail. There are extensive notes, and in the notes I've also derived the Taylor series for e to the x. A Taylor series is a power series that applies to a specific function where we can generate the power series by taking derivatives. These are two of the most well-known important ones, and I want to talk about what you can do to these to make your life a little easier when manipulating them. We derived this, and the derivation is not too terrible, but what if we had e to a power? And let's just say, I like to say e to the thing, where this is not just an x. Well, the formal way of doing it is to take extensive series of derivatives, evaluate them, and then go from there, which can be very, very difficult. But notice, that's the only thing I have to consider is where the x is ending up, meaning this form would just be this. So in other words, if I said I want to do e to the 3x squared, taking derivatives of this would be very long and time consuming. But this, I can simply do the following. Now, generally speaking, when writing a power series, you always keep the x separated from the coefficient. So I'll have 3 to the nth power in the numerator, and then x squared to the nth power here. That's it. We don't have to do anything else. Let's do something similar with the cosine function. Let's suppose I wanted the cosine, perhaps, of the square root of x. Now again, taking derivatives of this would take a very long time and be quite difficult, yet all I have to do is replace the x with the square root function. And the nice thing is, the square root of x when squared is just x, and then I'm raising that to the nth power. And I get this. We know a geometric series takes on the following form. If we start this one at 0, then we get the following terms, which we know will equal this total whenever the absolute value of r is less than 1. We've worked with these before. So the question is, what if I have a function that seems to have the same form as the result? Could I write this as a power series? Well, it turns out I can if I consider 2x as my r, because it's exactly the form of 1 over 1 minus r. So with that said, I can claim that this is equal to the series from n equals 0 to infinity of 2x raised to the nth power, or 2 to the n, x to the n. Now, this is not going to converge for all real numbers. It's only going to converge in the same situation where the absolute value of r is less than 1. So then I'll look at this and say, well, when will this happen? This will happen when the absolute value of x is less than 1/2, or negative 1/2 is less than x, which is less than 1/2. The really key here is this guy right here. I'm less interested in the interval in this case as I am just this number here. This 1/2 is called the radius of convergence, which is where the interval of convergence comes from. So we're going to do another example. Let's consider another example. This one a bit more complicated. The question is, can I make this look like the form 1 over 1 minus r? Well, the first thing I can do is factor out the 2x out of the top. But that 4 is kind of pesky. So at this point here, perhaps, if I multiply numerator and denominator by 1/4, I would find that this is equal to the quantity 2x times 1/4, or 1/2 x. Over here I would get 1 minus 1/4 x squared. And now we have our form. There's our r right there. So I can say the power series for this is just going along as a coefficient. So I can write the power series as g of x equals 1/2 x times the sum, 0 to infinity, of this quantity right here, raised to the nth power. Now what I need to do is manipulate that, but because I can multiply this inside the power series, I'm going to find that I get, first of all, let's go ahead and expand this. This will be 1 over 4 to the n times x to the 2n. I can bring this x inside. So now I'll have x to the 2n plus 1. Now, the question is what to do with the 1/2. I can leave it on the outside, or I can change 4 to 2 squared to the n. And if I do that, then I can multiply this 2 in there as 1 over 2 to the 2n plus 1. And now we have our power series. So the last thing to consider is what is the radius of convergence of this power series. So I need all values of x where this quantity here in absolute value is less than 1, which would be the same as saying when is x squared less than 4, which is when the absolute value of x is less than 2. So our radius of convergence in this case is 2.